Hello and welcome back to new day, new challenge of creating an AI chip. But today we will dive deeper into Systemverilog. Last time we got a challenge of how to think as an hardware developer, starting from the task description and setting requirements, and then drawing the RTL diagram and thinking of the types of the um, the used variables and what data type are going to be used, and also thinking about like the arrays and the loops. When can they be used to eliminate the application of code, and also like combinational logic versus sequential logic, which one makes sense in which logic. So this was more or less last time, and everything is written in text on paper without any coding. But of course, you need to know about the code itself in order to be able to implement it, even though um, like the implementation shouldn't be a problem if the description is written in details. Thank you so much for the support, and um, I think we are ready to go. Let's get started. All right, so now we will getting to know about the dynamic array, queues, associative arrays. So deeper into arrays. So we already have known how to create a static array with a fixed size, and now it's just time to get deeper into the flexible and dynamic.
So imagine building a verification test bench for a complex FPGA subsystem. The stimulus may vary, sometimes 4 packets, other times 40. So how do you model data that grow, shrink, and reorganizes at runtime? So Systemverilog dynamic arrays, queues, and associative arrays provide the flexibility that static arrays cannot. In this video, you will learn how Systemverilog declares and allocates dynamic arrays versus static arrays, explore dynamic array methods, new, delete, and size for runtime memory management, introduce queues for push, pop operations in TestBench, compare dynamic arrays and queues with examples of pushing, popping, inserting, and deleting elements. So by the end of this video, in TestBench, compare dynamic arrays and queues with examples of pushing, popping, inserting, and deleting elements.
So it reminds me in C++ about malloc and alloc heap variables. So actually dynamic variables, with also pushing and popping, and these realize how flexible the system Verilog is and how comparable it is with C++.
So by the end of this video, you'll be able to describe the difference between static and dynamic arrays and why dynamic memory is helpful in TestBench. You'll also be able to declare dynamic arrays, allocate memory with new, and manage runtime data using delete and size. And
Let's
then
repeat this word.
use queues for between static and dynamic arrays and why dynamic memory is helpful in TestBench. You'll also be able to declare dynamic arrays, allocate memory with new, and manage runtime data using delete and size. And then use queues for push, front, push, back, pop, insert, and delete operations. And finally, select the proper data structure dynamic arrays, queue, or associative arrays based on runtime need. So Systemverilog supports static arrays and dynamic arrays. So the static arrays are simple, but dynamic arrays provide runtime flexibility. So let us start by looking at how to declare a dynamic array. Here is the general syntax. You have type, variable name, and square brackets. So notice the empty square brackets. So this tells Systemverilog that the array size is not fixed, unlike static arrays where you specify the size in the declaration. So dynamic arrays start with no allocated memory. For example, we have logic 7 down to 0, example, and then empty square brackets. And then you now assign example to new 4. So let's break this code down. The logic 7 down to 0 defines each element as an 8-bit vector. And then the example square brackets declare a dynamic array with no initial size. And finally, the new 4 in square brackets allocates space for 4 elements at runtime. So because dynamic array starts empty, you must allocate memory before using them. So we do this with the new method specifying the number of elements we want. Dynamic arrays give us flexibility, but we also need ways to manage their size. So systems with the new method specifying the number of elements we want. Dynamic arrays give us flexibility.
So here is, of course, specifying the our allocate space at the runtime using this new, which means that the dynamic array example, I can reuse it this time with 4 elements in this part of code, but I can also have 7 spaces in other places or 7 elements in other places in the code. So it's actually its place is determined during the runtime.
You must allocate memory before using them. So we do this with the new method specifying the number of elements we want. Dynamic arrays give us flexibility, but we also need ways to manage their size. So Systemverilog provides several useful methods, including new, delete, and size. So new allocates or resize memory for the array, delete remove all elements from the array, and size checks how many elements are correctly in the array. So let's explore each of the methods in detail. So the new method lets us allocate memory for a specific number of elements. So you have name, size. Here, value is optional, which is letting you initialize array with data. So for example, to create a dynamic array of 8 elements, we write this. So this allocates space for 8 elements, index 0 through 7. And now you can read and write to any of these positions. Then, for instance, if we like to resize from 8 to 16 elements, we can write example is equal to new 16. So this creates an entirely new empty array. But if we want to keep the existing data, we can pass the old array as an argument. But what if you want to keep your existing data? Pass the old array as an argument. So example is equal to new in square brackets 16 in curly braces. This is an example to resizes while keeping the existing data. So this way, the original 8 elements stay at the beginning of the new array and the remaining positions are empty. Now, dynamic arrays are incredibly useful in test benches where the number of elements is not fixed, and mastering methods such as new and delete is essential. For 8 elements, index 0 through using them. So we do this with the new method specifying the number of elements we want. Dynamic arrays give us flexibility, but we also need ways to manage their size. So Systemverilog provides several useful methods, including new, delete, and size. So new allocates or resize memory for the array, delete remove all elements from the array, and size checks how many elements are correctly in the array. So let's explore each of the methods in detail. So the new method lets us allocate memory for a array, delete, and size. So new allocates or resize memory for the array, delete remove all elements from the array, and size checks how many elements are correctly in the array. So let's explore each of the methods in detail. So the new method lets us allocate memory for a specific number of elements. So you have name, size. Here, value is optional, which is letting you initialize array with data. So for example, to create a dynamic array of 8 elements, we write this. So this allocates space for 8 elements, index 0 through 7. And now you can read and write to any of these positions. Then, for instance, if we like to resize from 8 to 16 elements, we can write example is equal to new 16. So this creates an entirely new empty array. But if we want to keep the existing data, we can pass the old array as an argument. But what if you want to keep your existing data? Pass the old array as an argument. So example is equal to new in square brackets 16 in curly braces. This is an example to resize this while keeping the existing data. So this way, the original 8 elements stay at the beginning of the new array and the remaining positions are empty. Now, dynamic arrays are incredibly useful in test benches where the number of elements is not fixed, and mastering methods such as new and delete is essential. Size will make your arrays more flexible and powerful. Next, delete method. So in Systemverilog, we use the delete method to remove all contents of a dynamic array. So when it's called, it not only clears the element, but it also deallocates the memory, similar to the free function in C. The syntax is simple. You have name, delete. For example, suppose we allocate the memory. We use the delete method to remove all contents of a dynamic array. So when it's called, it not only clears the element, but it also deallocates the memory, similar to the free function in C. The syntax is simple. You have name. It not only clears the element, but it also deallocates the memory, similar to the free function in C. The syntax is simple. You have name, delete. For example, suppose we have a dynamic array of 8 elements. So after calling delete, your array is completely cleared, the size becomes 0, and the memory is released. So you can allocate new memory with new keyword if needed. The size method. So to find out how many elements a dynamic array currently holds, we use the size method. So it returns the current number of elements, just like the size macro for static arrays. So the syntax is name, size, and brackets.
Example: this method is advantageous when working with dynamic arrays in your test bench.
Now that you've understood dynamic arrays, let's explore queues, which is another powerful data structure in Systemverilog. So queues are another type of dynamic arrays, unlike regular dynamic arrays. Queues automatically resize when you add or remove elements. So here's how you declare a queue. You have type, variable name, and then the size. So the dollar symbol indicates that is a queue. The max length is optional. If omitted, the queue is unbounded, meaning it can grow without limits. So queues with a set maximum are called bounded queues. So for example, you have a bounded queue and an unbounded queue. So the bounded queue has a limit of 255, while the unbounded queue has no limit, just the dollar sign in the brackets. So why should you use a dynamic array versus a queue? Let's compare them. So dynamic arrays and queues are similar. They are both allocated at runtime, but they're optimized differently. Queues are fast for adding or removing elements at the front or back, similar to a linked list, which is perfect for FIFO or LIFO operations in test. Bounded queues. So, for example, you have a bounded queue and an unbounded queue. So, the bounded queue has a limit of 255, while the unbounded queue has no limit, just the dollar sign in the brackets. So, why should you use a dynamic array versus a queue? Let's compare them. So dynamic arrays and queues are similar. They are both allocated at runtime, but they're optimized differently. Queues are fast for adding or removing elements at the front or back, similar to a linked list, which is perfect for FIFO or LIFO operations in TestBench. Why? Dynamic arrays are better for accessing elements in the middle, since all components are stored contiguously in memory. So by mastering dynamic arrays and queues, you gain the flexibility needed to model real-world, unpredictable data flows in verification environments, making your test bench more powerful, expressive, and closer to how real hardware systems behave. So in summary, let's do a quick recap of the key learnings from this video. So here's what we've learned. We learned that static arrays have a fixed size, while dynamic arrays can grow or shrink during simulation. We also learned that dynamic arrays use and require new to allocate memory. Delete clears a dynamic current element count. Queues auto resize, which is ideal for FIFO or LIFO operations. Queue method like push, pop, insert, delete allow flexible elements manipulations. Now, I have a question for you.
The instructor has spoken about various external resources and links during the course. In the following section, you will find the links and site information related to lesson topics. Article: Design and Verification of Asynchronous, First in First Out FIFO. This paper is about designing and verifying asynchronous FIFO memory, a key component for temporary data storage and reliable data transfer in digital systems using Systemverilog. The FIFO design handles read and write operations, full and empty flags, and pointer management, implemented in Verilog at the RTL level.
When building our calculator design, we need a clean way to represent everything, from simple logic operation like and, or, to arithmetic functions like addition and subtraction. So instead of writing long, messy expression, Systemverilog gives us a rich set of operators that lets us model these behaviors clearly and efficiently. Understanding these operators is key to implementing a calculator that is easy to read, easy to debug, and cleanly maps to hardware. In this video, explore the when building our calculator design, we need a clean way to represent everything, from simple logic operation like AND, or to arithmetic functions like addition and subtraction. So instead of writing long, messy expression, Systemverilog gives us a rich set of operators that lets us model these behaviors clearly and efficiently. Understanding these operators is key to implementing a calculator that is easy to read, easy to debug, and cleanly maps to hardware. In this video, explore the different operator categories available in Systemverilog, explain the difference between relational versus logical operators, and when to use each. Then walk through shift operators, the conditional ternary operators, and how they map to hardware. And finally, illustrate how concatenation and replication help you build buses and manipulate vectors efficiently. And by the end of this video, you will be able to identify when to use bitwise logical, arithmetic, or relational operators in vectors efficiently. And by the end of this video, you will be able to identify when to use bitwise logical, arithmetic, or relational operators in your design, recognize which operators synthesize safely and which are simulation only, apply shift and conditional operators to simplify arithmetic and decision logic, and finally, use concatenation and replication to construct reshape multi-bit buses cleanly. So let's break them down category by category using examples of operation in our calculator model. So we'll start with the bitwise operators, the foundation of all digital logic. So the bitwise operators act directly on individual bits. Operators like AND, OR, XOR, NAND, NOR, and NOT all fall into this group. So for example, in our calculator model, we set one of the many logical or bitwise operations to the result of a logical operation. Shift operators. The shift operators move the model we set one of the many logical or bitwise operations to the result of a logical operation. Shift operators. So shift operators move bits left or right, but they are often used for tasks like scaling values, aligning fields, or building arithmetic hardware. Example from our calculator model. Then we have the conditional operators. The conditional operators, often called the ternary operators, they let us choose between two values based on a condition. So you probably seen it in C or Java. It looks like this. So you have your output is equal to the condition, and if the condition is true, you get the value if true or value is false. This is the syntax for the ternary operator. So in this statement, the condition is evaluated first. If the condition is true, expression returns value if true. Otherwise, it returns value if false. So the selected value is then assigned to the output, making this a compact way to express simple decision-making logic in hardware. So for example, in our calculator model, if the OP group bit is 1, we set our state to a logical operation. Otherwise, we set it to an arithmetic operation. So this way, we can switch between logical and arithmetic operation. State to a logical operation. Otherwise, we set it to an arithmetic operation. So this way, we can switch between logical and arithmetic operation. Relational operators. Relational operators lets us compare values. They return true or false, represented as 1 or 0. So if you've used languages like C or Java, this will look familiar to you. Greater than, less than, greater than or equal to, equal, and not equal. We will implement them in our logic. So for example, in our earlier sum model, under the arithmetic operation, we are performing relational comparisons between the two inputs, A and B. So when the operator code is set to, for example, 3 binary 0, 1, 1, the LU checks whether A is greater than B. If the condition is true, the result is set to 1. Otherwise, it outputs 0. And with the value 3B100 performs the opposite comparison. So it checks if A is less than B, again producing a 1 for true, for false. And when the opcode is 101, we compare the two values for equality. So if A equals B, it outputs 1. If they are different, it outputs 0. And finally, if it's 110, we check for inequality. If A and B are not equal, the result is 1, otherwise is 0. So in all of these cases, isn't generating a new numeric value. It's answering a yes or no question about the relationship between A and B using a single bit result to represent the outcome. In our register sum model, we can set two signals, empty and full, detect when our FIFO is full or empty. And this is when the read pointer equals the write pointer. So is the FIFO's initial position, or it means the FIFO is empty. The FIFO becomes full when the write pointer or register B reaches register A, or when the read pointer reaches register A by 1. This means it will override the read pointer on the next push. So next we have arithmetic operators, including addition, subtraction, multiplication, division, and more. So most synthesis tools can handle addition and subtraction and multiplication, though efficiency can vary. So for example, from our calculator model for arithmetic operation, in this part of the LU, we are performing relational comparison between the two inputs A and B. So when the operation code is set to 011, the ALU checks whether A is greater than B. If the condition is true, the result is set to 1. Otherwise, it outputs 0. With 100, the ALU performs the opposite comparison. It checks if A is less than B, again producing a 1 for true and 0 for false. And when the opcode is 101, we compare the two values for equality. If A equals B, the ALU outputs 1. If they are different, it outputs 0. Finally, 110 checks for inequality. If A and B are not equal, the result is 1, otherwise is 0. Logical operators combine relational expression to form more complex condition. So where bitwise operators act on the bits themselves, logical operators act on a true-false result. So Systemverilog gives us the logical and, logical or, logical not. So for example, in our calculator model, we have to combine multiple conditions before pushing values or popping out values from our FIFO. So before we push, we make sure the push FIFO signal is set and that the FIFO is not full. So to pop, we make sure the pop signal is set and that the FIFO is not empty. That is, it contains at least one entry. Now let's do a quick recap of the key learnings from this. We make sure the pop signal is set and that the FIFO is not empty. Bitwise of a logical and, logical or, logical not. From this video. So here is what we've learned. Bitwise operators model logic gates by acting on individual bits. Shift operators move bits, and arithmetic operators perform calculation in the area. Relational operators complete at least one entry. Now let's do a quick recap of the key learnings from this video. So here is what we've learned. Bitwise operators model logic gates by acting on individual bits. Shift operators move bits, and arithmetic operators perform calculation in the area. Relational operators complete by acting on individual bits. Shift operators move bits, and arithmetic operators perform calculation in the area. Relational operators compare values, while logical operators combine conditions for control. The conditional ternary operators select values based on a condition. Before we wrap up, let's test your understanding with a quick question.
So by using dynamic array, resetting will be easy because I can simply delete it. So
Now, imagine your design is getting bigger, more states, more signal, more repeated patterns, and suddenly the built-in system Verilog data types aren't enough. So at this point, you need clean, reusable custom types to keep your code readable and your state machines organized. So in this video, we'll show how to create custom data types using type def, enums, and struct. We'll demonstrate how type def simplifies complex types and array declarations. We also explain how enums make state machines safer and how to set custom encodings. Then we'll cover practical enum methods like prev, next, first, last, and name. And finally, we will illustrate how struct groups, related signals, and when a union might be appropriate. So by the end of this video, you'll be able to illustrate how struct groups, related signals, and when a union might be appropriate. So by the end of this video, you'll be able to explain why type defs improve readability and reuse in RTL and test bench code. Define enums for state machines, including both default and custom encodings. Use enum methods to navigate or inspect state values during simulation, and also build structs that bundle related signals together and understand how unions are appropriate. So now let's start with type def, the foundation for creating reusable type definitions. So we use the type def keyword to define a new type in Systemverilog. So this is very similar to how C or C++ allows you to create custom types. So here is the general syntax. For example, if Systemverilog, so this is very similar to how C or C++ allows you to create custom types. So here is the general syntax. For example, if we want an 8-bit logic type, we could write type def logic a square bracket 7 down to 0 and the name logic 8. So in this example, we are creating a new type called logic 8. And by using type def, we tell Systemverilog that logic 8 is just another name for an 8-bit logic vector. So this makes our code easier to read and lets us use the same definition wherever we need an 8-bit signal. So now we can declare the variable using this new type. So we write logic 8 example, so which is equivalent to logic 7 down to 0 called example. So type def with arrays. Now we can also create custom array types with type defs. So to do this, we append the number of elements at the end. So for example, you have type def logic 7 down to 8. The name is logic 8 array, and it has 4 contents, 4 values. Or we specify explicit indices, just like we write here, 3 down to 0. Type def logic 7 down to 0, logic 8 array, 3 down to 0. So once declared, we can create variables and access elements like normal arrays. Next, we have enumerated types. So enums. Enums allows us to define a set of valid values for a variable. So this is especially useful for state machines, which we are going to use in our code. So for example, in our calculator, values for a variable. Next, we have enumerated types. So enums. Enums allows us to define a set of valid values for a variable. So this is especially useful for state machines, which we are going to use in our code. So for example, in our calculator, we can decide to define a simple finished state machines, which are enums. Enums allows us to define a set of valid values for a variable. So this is especially useful for state machines, which we are going to use in our code. So for example, in our calculator, we can decide to define a simple finished state machine with 3 states in our code.
All right.
So for example, in our calculator, values like normal a variable. So this is especially useful for state machines, which we are going to use in our code. So for example, in our calculator, we can decide to define a simple finished state machine with 3 states. So we have the first state, logic OP. So logic operation is encoded as state 0. And in this state, we handle all logic operations. Then we have arithmetic OP, or arithmetic operation, is encoded as state 1. Here we perform only arithmetic operations. And then finally done for state 2, which tells us the operation is finished. So this lets us clearly separate functionality. Each state handles a single category of work. So we create a custom enum type called state underscore t to represent these states. And then we declare a variable state to hold the calculator's current state. So let's look at how enums values are assigned by default and how you can customize them. So when we create an enumerated type in Systemverilog date. So this lets us clearly separate functionality. Each state handles a single category of work.
Yeah, so basically, when I like for any logic, there are in hardware, there are kind of basics that you have to think of in order to perform your logic in a correct way. So final state machine is one of the basics, right? So in any logic, you need a final state machine, okay, because you're dealing with signals and time is limited. So you wanted to put it in a way that this is doing that or this, so they both can't be done in the same time. And I wanted to see in which state your logic is at. So final state machine final state machine is from the basics of building like a working logic, right? The second thing would be allos. Yeah, so most probably you are doing performance, whether the allo is, whether it is an arithmetic operation or a signal, like bitwise operation, like logical operation. So there could be also some debounce, some signal processing, I don't know, filtering, right? There could be some, and then there could be storage, right? So this storage could be a FIFO, which we're gonna be learning later, how to build a FIFO. And there is a very interesting paper that writes about how to create a FIFO. So this is from the basic to, yeah, to build any logic. So those are kind of your tools that you already knows. Okay, this is in my pocket. With that, then you can build the logic out of it. Okay, so and then for final state machine, the first thing to think of is an enum, right?
So we create a custom enum type called state underscore t to represent these states. And then we declare a variable state to hold the calculator's current state. So let's look at how enums values are assigned by default and how you can customize them. So when we create an enumerated type in Systemverilog, it automatically provides a set of useful methods for working with enum values. So these methods include the prev method, which lets us move in the previous value in the enum list, while next advances to the next value. If we need to jump to the boundaries, first returns the very first enum value,
and last returns the final one. Then finally, the name method returns the string name of the currently selected enum value, which is especially useful for debugging and readable output in test benches. So let's take a closer look at how each of these methods work. The previous method. The previous method lets us navigate through the constants in an enum. So by default, next return returns the constants at the current position, and prev returns the previous constants. So we can also jump multiple steps by passing an argument constants at the previous method. The previous method lets us navigate through the constants in an enum. So by default, next returns the constants at the current position, and prev returns the previous constants. So we can also jump multiple steps by passing an argument to the method. For example, passing 3 will move 3 elements forward or backward. So here, multiple steps by passing an argument to the method. For example, passing 3 will move 3 elements forward or backward. So here, assuming the current state is logic OP, we can use built-in enum methods to navigate through the state values. So by calling state.prev, we'll move to the previous enum constant, which in this case results to done, while state.next moves forward to arithmetic OP. So now with understanding of enums, let's look at structs and union, powerful ways to group related signals together. So here is the general syntax for a struct in Systemverilog. To create a union, we just replace the struct keyword with union. So in this declaration, we have type, which specifies the data type of each number, name, which gives a unique name to each member, and then the variable name, which creates a variable of the struct type. So we can include as many members as we need, and each member can have a different data type. Now let's see a practical example. Suppose we want to represent the RGB value of a pixel. So we can declare a struct with 3 8-bit members, one for red, green, and blue. This concludes the part 1 of the video customs types, typedef, enums, struct. Up next, customs types, typedef, enums, struct part 2. Welcome to part 2 of customs types, typedef, enums, structs. So let's take a look at how our state machine switches between different states, handling both arithmetic and logical operations. So we are going to define distinct operations for each state. And finally, we present our registers as an array. So in this example, we are going to learn how to use type def in Systemverilog, which lets us create new type names for convenience and readability. So first, we define a simple type called a byte t. So for an 8-bit logic, you can see the 8-bit is the bell 7 down to 0. And then, so this is exactly the same as writing the logic, uh, this logic on this line by T, A, and E. So, but using a type def is going to make the code cleaner and easier to maintain. So next, we define a type for an array of 4 16-bit words. So on this line, I see where we define the array. So here, mem, so followed by this mem is an array. So this is an array of 4 16-bit elements. And then we start assigning A to this 8-bit value and then B to this 8-bit value. So finally, we print everything here. So from what you could see here, this is a type def of type byte C, and then this is a mem also. A and B are type def of type byte C, and then mem is of type def word array T. And then here we are sending values to them, A, B, and also in mem, we are sending value here. And then finally, we display them here. So for this example, the key takeaway is that, type def will enable you to create meaningful type names, making the code cleaner and easier to read. So you can see how we created these different types. So when I run the code, let me show you the output. So you can see where we've displayed all the output for A, B, and for mem. So in this example, we are going to learn how to use enumeration, so enum in Systemverilog. So they are perfect for representing a finished state machine, like the one we used in our calculator. So first, we define a 2-bit enum called the state t, and you can see the types within them. You have the idle, read, write, and done states, and they're all assigned to values 0, 1, 2, and 3. So it they're all of 2 bits. You can see the 2 bits labeled 1 down to 0. So we can assign and inspect states easily here by creating a state here called the state, which is of type the state T, which is our enum, which we created just above here. And we can query the first and last state. So we first of all set our state to idle, which is the first state. And then here we'll display the initial states here. Next, remember, we're going to use next and prev to iterate to go up or down within our enum. So when we set the state to state.next, it's going to move from idle down to read. And then when we do state is equal to state.previous, it's going to move back from read back to the idle. So then finally we'll display the first state and last state using the state.first name and state.last name to display done, which is the last, and then idle, which is the first. So I will run this code now. I'll show you the output. So the key takeaway is that enums make finished state machines is design readable, type safe, and easy to navigate. So you can see our output down here. Our initial state, our next state, previous state, the first and last state. So in this short example, we'll see how to use struct in Systemverilog. So with struct, we're able to group related data together. So it's more like a container. and it's useful for modeling things like maybe packets if you're doing networking on FPGA for packets, buses, or records. So here we define a struct called a packet T, and then we packet T is going to represent a simple data packet, and it's we have three fields. It will have the address, the data, and valid within it. You can see the address is 8 bits, data is 8 bits, and valid is just a single bit. So by marking it as packed ensures that all the fields are stored. So we refer it as we by marking it as packed here. So the packed is not compulsory, but if you mark it as packed, Systemverilog will ensure that all the fields are stored contiguously in memory, which is important for hardware mapping and bit level operation. So we declare a variable called packed EKT of type our struct packets. So the single variable now contains all the three fields, so we can access and modify them individually. So here you can see how we access each of them. So first we set a value for them. So we assign a value to each of them, and then we display their values here. So you can just call them up to reference their value. So let me run it. So the main key takeaway here is that struct groups related signals together, and when we have a packed struct, it ensures that contiguous memory layout, which is useful for hardware synthesis. And you can as well assign and access and modify each field. And they're especially helpful uh, for modeling packets and interfaces. So you can see our value, the values of our structs here. And then finally, for this last example, we'll learn about union in Systemverilog. So they're similar to structs, but just that instead of writing struct, we write union. So we also have a packed union. So, but they store different types of data in the same memory location. Unlike struct, where each field gets its own memory, a union lets multiple fields share the same memory. So writing to one field affects all the other fields. Here we define a packed union called the word union C down here. And then we create a value of that type. We just write the call it U. So here you can see all these values. It means that here we have word, which is 32 bits, and then we have bytes, which is an array consisting of four elements, which is 7 down to 08 bits by 4 is also equal to 32. So both of them are shared in the same space. So it's more like a union, either this or this, either word or bytes. So this means word and bytes, this word and bytes occupy the same 32 bits in memory. So you can either treat it as one 32-bit integer or as a 4-bit separate byte types. So next we declare a variable u of type union. So we first assign a 32-bit value to the word down here. So then we display it down here. And then we assign another bytes. So at this point, the 4 bytes in byte 0 to byte 3 reflect the individual bytes of the 32-bit word. So now comes the interesting part. We modify just 1 byte here. So remember, 4 bytes make up 1 word. So we fill up the whole word with 32-bit value, and then we just change only 1 byte here, and then we display it. So we're just changing by 0. So remember that both the byte and the word are sharing the same space. So, but the word is 32 and the byte is just 8 out of 32. So we are replacing just one of the bytes, not 4 of them, and then we'll display them. So this is the very good use of union. So when you want to replace some part of a value, you use a union. So union will share memory between all the fields, and modifying one field affects all other fields. So union lets us interpret the same data in multiple using in multiple ways. So union as compared to struct is very useful for byte level manipulation or hardware memory efficient memory usage when you want to like access some parts of memory or make changes to it. So you can create the same assign the same memory uh, address to different values within the union. So in conclusion, typedef, enum, and struct lets you create clean, reusable, and organized Systemverilog code. They simplify declarations, group related signals, and define state machines, making design easier to read, debug, and maintain, which is essential for professional RTL and verification work. Now, let's do a quick recap of the key learning from this video. So here is what we learned. Type defs create reusable type aliases for simple declarations. Enums define named constants, ideal for readable state machines with methods first, last, next, previous name for navigation and debugging. Struct groups related signals with independent storage, while union shares memory for alternative interpretations. So these custom types enhance readability, they reduce errors, debugging. Struct groups related signals with independent storage, while union shares memory for alternative interpretations. Group related signals with independent storage, while union shares memory for alternative interpretations. So these custom types enhance readability, they reduce errors, and simplify maintenance in complex design and test benches. So now I have a question for you.
So yeah, why didn't I choose it? Because I thought it has to use the logic 3 down to 0 after the enum, but looks like it can be also used without the logic. So okay. Thank you for the comment.
Every calculator is logic gates that compute and or and not operations plus multiplexers that route data between models. Every calculator needs logic gates that compute and or and not operations, plus multiplexers that route data between models. But here's the challenge. How do you describe the combinational logic in Systemverilog without writing verbose repetitive codes? The answer lies in continuous assignment, a clean expression-based approach that keeps your design compact and your signal always up to date. So in this video, we'll show you how to use continuous assignments in a Systemverilog for combinational circuits, explain explicit continuous assignment with the assign keyword, and implicit net declaration assignment. We'll demonstrate modeling basic gates arithmetics and logic operation using bitwise and conditional operators. Explore building multiplexers using conditional operators and arrays for create how indexing arrays and concatenation can simplify multiplexer modeling. So by the end of this video, you'll be able to differentiate between explicit continuous assignment and implicit net declaration assignment in Systemverilog. Implement combinational logic gates using bitwise operators and continuous assignment, and construct 2-to-1 or 4-to-1 multiplexers using the conditional ternary operators. And finally, apply arrays and concatenation to organize inputs and outputs efficiently in combinational design. And then the two forms of continuous assignment that Systemverilog supports. The first one is explicit continuous assignment using the assign keyword. And secondly, the implicit continuous assignment, also known as net declaration assignment, where a value is assigned right in the declaration. So let's take a look at each approach. So to explicitly assign a value, continuously we use the assign keyword. The basic form looks like this. You have assign, the variable, and the value. So the value on the right can be a constant or an expression using Systemverilog operators. So whenever anything in that expression changes, the assign signal updates automatically. So for example, in our area, we use the opcode signal to keep track of the current opcode from the operand bit 2 down to 0. An op group which switches between logic and arithmetic operation using the 3 of the operand. So here, the signal OP group always tracks the value of operand 3, and opcode always tracks operand 2 down to 0. So once the right signal changes, the left signals update. In our FIFO, we also set the empty and full signal using assign. In these examples, empty and full are continuously updated based on the values of register A and register B. So this ensures that the FIFO status signal always reflects the current state of the registers without needing a separate procedural block. So now let's talk about net declaration assignments. So Systemverilog also lets us assign a value when a signal is declared. So this is known as a net declaration assignment, and it can help reduce code clutter. So the syntax looks like this: type, a variable, and a value. So for instance, you can say logic A is equal to B. Functionally, this behaves just like the explicit assignment statements. It's simply more compact. So with these assignment techniques in hand, let's see how to model one of the most common combinational components, multiplexers. Multiplexers are common combinational components, and Systemverilog provides several ways to model them. One approach always uses blocks, but we save that for later. In this lesson, we focus on simpler expression-based methods. So the conditional operator provides a clean, intuitive way to build multiplexers. So using the conditional operator, Systemverilog includes a conditional operator just like C tenary's operator. The format is this: you have output is equal to condition, question mark, value if true and value if false. So a 2-to-1 multiplexer is a perfect example. In our top model, we have two inputs, data 1 and data 2, and one output, the LU result signal. So to store data in the FIFO using the FIFO in signal, we use a multiplexer with a select signal that selects between data 1 and the LU result to store in our register. So the LUA and LUB inputs use the select A and select B signals respectively to choose between the input data and the output from our FIFO. So this is a good demonstration of the use of a multiplexer. So let's now see how we can apply our knowledge of continuous assignment in the code.
So in this example, we'll learn about continuous assignments in Systemverilog using the assign keyword. So this is the assign keyword here. So we have three input signals, A, B, C. And one output Y. So we use an explicit continuous assignment to define Y. So in terms of the inputs, so here Y will always reflect the current values of A, B, and C. So this expression you are seeing here, this logic expression here, is evaluated continuously in a loop. So it will keep checking for the values of A, B, C, and then be calculating this logic here, evaluating this logic. Then in the initial block, we assign some values to the input. So here we assign A1, B0, and C1, and then we print out their values here. So one way you can tell there is a continuous assignment is the use of this equal sign. So this is what makes it a continuous assignment. So, but in our next example, you will see the other type where we do something like this. So that is not a continuous assignment. So for this, when we run it, it will just evaluate our logic here: A equal to 1, B equal to 0, and C is equal to 1. So if you run this logic, you will get the output. But the key takeaway is that for a continuous assignment, it will always get the value of Y repeatedly from A, B, C, or steadily using this equals sign is what makes it a continuous assignment. So in our last example, we learned about the explicit continuous assignment. Now, in this example, we're going to learn about the implicit continuous assignment. So it's just the basic difference between the two of them here. For implicit, you just define the variable, you define it, not A and B, and then you assign a value to it immediately. But for the explicit, you first of all define its y here, and then you start assigning a value to it. So the key takeaway here is that the implicit assignment, which is this one, it doesn't use the assign keyword. So once you define the variable, not A and B, you assign a value to it. That's what makes it implicit. So it lets you to declare combinational logic directly, and the signal updates automatically whenever the input changes. So this will make the code more simpler and cleaner to read. But for the explicit, which was the initial assignment I showed you here, the explicit uses the assign keyword. So you first of all define the variable before you now use the assign keyword to assign a value to it. So let me run it. So in short, the Systemverilog allows you to write combinational logic elegantly. So either with the assign or direct with the logic declaration. So both the explicit and the implicit, they all work and providing us with the same value. This concludes combinational logic, continuous assignment, part 1. In this video, you have learned continuous assignments and system failures in assigned keywords. Coming up, implement a multiplexer using the conditional operator. Welcome back to combinational logic, continuous assignment. Part 2, implement a multiplexer using the conditional operator. So next, in this example, we're going to learn how to implement a 2-to-1 multiplexer in Systemverilog. So here we have 3 inputs, D0, D1, and our select, and one output, we call it Y. So we're going to define the multiplexer using the conditional ternary operator, which is this question mark here. So this means that if this cell is equal to 1, then we assign Y to D1. Otherwise, Y takes the value of D0. So this is the basic multiplexer, how to define a multiplexer using this ternary operator. So in the initial block, we first set the inputs D0 to 0, D1 to 1, and our select to 0. So this line on line 7, this is where we'll set them. So we first of all display all their values here. Then we change our select to 1 and then display their values here. So the idea is to show you the value of Y as select changes. So this is basically how multiplexer works. So we control Y using select. We assign these two values to Y using the value of this select. So now I run it. So you can see the values here. So when select is equal to 0, Y is 0. When select is 1, Y is 1. 2 and 1 reflects the value of D1 and D0. So finally, in this example, I'll demonstrate the 4-to-1 multiplexer in Systemverilog. So here we have 4 data inputs, D0, D1, D2, and D3. And then we have one output, which is Y. So we define the multiplexer using the nested conditional operator. So instead of a single ternary operator, we use a nested ternary operator. So let me quickly just put them in one line so it looks clear. Here you can see that we are using 2 bits to switch the value of select instead of the single 1 bit we used in our last lesson. So here, so we define the multiplexer using nested condition. So this means that if the select is 0, we assign y to this value. Else, if select is equal to any other value, we'll come to this section here. So this is one statement here. If select is equal to 0, we assign y to d0, whatever the value of d0 is. Else, we run this second statement. So it's different from the 2 to 1 multiplexer. Now, when we get to the second statement, we are going to run this one again. So these are nested. So we run them sequentially, one after another. So we run this one, we check again. If select is equal to 1, we set y equal to d1. Else, we come to this next statement again. So we run this sequential again. We run this first line again. If select is equal to 1, 0, which is 2, we set y equal to d2. What else comes after that? We just set y equal to d3. So next, we assign values to d0, d1, d2, and d3, and then we print them. So let me run it. So this is just the 4 to 1 multiplexer. You can also use this same method to do an 8 to 1 multiplexer. So this is what our output code looks like. So remember, we set d0 to 0 and d2 to 0. So if you were asked what's going to happen if select is equal to 2, if out of a 8 to 1 multiplexer, so it means that select is going to be 3 bits. So that is it for this demo. Thank you.
Now, I have a question for you. So let's do a quick recap of the key learnings from this video. Continuous assignment models combinational logic by keeping output signals automatically updated whenever input expression change. Explicit assignments use the assign keyword, while implicit net declaration assignments combines declaration and assignments in a single line for a cleaner code. Bitwise operators with continuous assignments let you implement logic gates like AND, or, not, and ZOR. The conditional ternary operators provide a compact way to model multiplexers, selecting between inputs based on a control signal. Now, I have a task for you. In this lab called Applying Combinational Logic to FIFO Design, you'll be given a basic template for the FIFO push and pop logic. Now, use any if-else structure of your choice to complete the implementation. Continuous assignment is a fundamental technique for modeling combinational logic in Systemverilog. So whether you use explicit assignment statements or implicit net declaration assignments, both approaches keep your signal automatically synchronized with the input expressions. So combined with the conditional operators for multiplexers and bitwise operators for logic gates, you now have the essential tool to build a clean, efficient combinational circuit, precisely what we need for our calculator LU and data routine logic.
All right. So um, that was the basics, the second basics of Systemverilog, which is like a core base to build an AI chip. And looks like also building calculator can be more optimized using dynamic arrays and so on. So um, I hope we have learned something in this video. Thank you so much for following and see you next time.